This is the Calculus A-B speed review.
Okay, so to start off the calculus crash course, we're going to be doing limits, and limits are essentially calculus, and if you don't know what they are, you're essentially screwed. So, limits define the continuity that'll cover. So limits define continuity of a function that I'll cover in a little bit, and then we'll go more in depth with limits and their effects on things later, as Shannon and Sarah will talk to you about. So a limit is just any point on a function where the function approaches said point, and even if it's not on the graph f of x, it's just where the point would be. So a function's limit can either just be a simple number, not exist, or a value of positive or negative infinity. And so to start off with the number, we're going to have just a simple function f of x as x squared plus 2. As the limit of f of x approaches 1, we see that it hits the point y equals 3, which can also just be shown by plugging in the point f of 1 equals x squared plus 2, which equals 1 squared plus 2, which equals 3. So then you get your limit as x approaches 1 of f of x equals 3. The other form of a limit that we can find is when it approaches infinity or negative infinity. So if we look at the graph y equals 2 to the x, then we get something that looks a little bit like this. And if we have, as the limit approaches as x approaches negative infinity, then we get it approaches 0, because the graph just gets smaller and smaller and smaller and smaller until it would reach 0, but it doesn't actually. So a limit is where it could reach, but it doesn't necessarily mean that it will reach that point. And then finally we have when a limit does not exist, and this is usually with a piecewise function. So look at the limit as x goes to 1, or as x goes to 0, then we see that there are actually 2 points that x is supposed to equal. So they're not, and because of the rules of discontinuity, where both points have to actually exist, and then 2 is that both limits have to exist, and then 3 is that all of these, or the limits of f of x and of g of x, which would just be either of the functions within the piecewise function, are equal. And so as you can see here, they're clearly not equal, meaning that as the limit f of x approaches 0, it's not real.
So, in short, the derivative is a function which represents the average rate of change of the original function. For example, this is f of x. F prime of x would be a graph that measures the slope of a tangent line, or the rate of change of the entire function. It is sometimes, well, it's possible and also sometimes more useful to find the rate of change at a given point. That's the rate that the function is changing slope at that particular point. Instantaneous, because rate is equal to the change in distance over the change in time, it's very hard to find this, and we come to our first problem that calculus tries to solve, because the distance in between one point and itself is 0 over time, which there is no time because it's 1 point, so you get 0 over 0, which is absolutely useless, and you can't find any rates from that. But if you use the idea of the limit that Elena talked about earlier, you can approach from both sides, cover up this point, and find most likely the slope of that point. Now, to find the derivative, there are a few different ways you can do that, but the fail-safe way is m, that would be the derivative, or y prime, is equal to f of x plus h minus f of x all over h. Now, this is the limit as h approaches 0. Now, this uses the idea of a limit that we talked about earlier on the graph, and finds an algebraic way to shrink down that distance until you find where it is equal to 0. There are also a few other different ways that you can find some shortcuts if that's a really nasty function for you to write out, including the power rule, also the quotient rule, and for when you have a function that has two different variables like that, or a product rule for when you have an x times y to find the derivative of that. Oh, you can also use, for when you get 0 over 0, L'Hopital's rule, which is very useful, and you can keep taking the derivative until you end up with something useful. Now that we know how to find the derivative, what we can do with it? We can find a function's critical points. So we have function f of x here. We can find the critical points. Now the critical points are where derivative is undefined or equal to 0. So that's where the tangent line is equal to 0. So that would be about here. And with critical points, we can find the max and min value of a function, which is where it has its lowest y value and its highest y value. These are also known as extrema. There's relative extrema and absolute extrema. Relative being, if there was a function like this, a relative maximum would be right here, where it's not the absolute maximum, but it is still a point where the derivative changes from being positive to changes to being negative. Now we can use extrema to help with optimization problems. Now, with a derivative, you can also take the derivative of the derivative. So if there was a graph of all these slopes, you could take then the slopes of the slopes, and that would be the second derivative, and then the slopes of all those slopes, which would be the third derivative. Now these multiple derivatives can be used to tell more things about this graph. You can find where it is concave up using the second derivative you can find its points of inflection, which is where a graph would change concavity, which would be right here. To find any of these critical points of inflection, you would set derivative or second derivative equal to 0 and solve for x. These now third derivatives are not really useful for this, but they can tell you a lot about particle behavior. And if a particle is moving like this, the first position, this would be a position graph. The second derivative, or p prime, would be equal to the velocity, and the second derivative would be equal to the acceleration, and the third derivative would be equal to the jerk.
Okay, so the mean value theorem states that if f of x is differentiable and continuous on the interval a to b, then there is at least one point c where the derivative of f of c is equal to f of b minus f of a over b minus a. So you might recognize this as the average rate of change, and also the equation for the secant line, which would look something like this. And then, so this theorem states that at f of c, if you find the derivative, you will also find the tangent line, and according to this theorem, there's one point c where the tangent line is equal to the average rate of change, or the secant line, and the instantaneous rate of change is equal to the average rate of change. So say there's a function f of t with bounds a and b, and if we add another bound x, let's say there's a function capital F of x, which equals the integral of a to x of f of t dt. Now this basically states that there's a function capital F of x, which is equal to the area under the curve of f of t between the bounds a and x. Now the fundamental theorem of calculus states that if you find the derivative of this capital F of x, then that equals the derivative of this integral, which equals f of x. Now this is so fundamental in many ways. First of all, it relates integrals to derivatives, and it shows that we can find the derivative, we can find the antiderivative of any function. So by using the fundamental theorem of calculus, we can find antiderivatives and we can solve for areas under the curve. So the second part of the fundamental theorem of calculus states that the integral of a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x, the derivative of that equals f of x. So that means if you find the derivative, you can find the area underneath that curve. So an example would be from 1 to 2 of x squared dx will be equal to the antiderivative, derivative, which is x cubed over 3, and you do this, 1 to 2 equals 2 cubed over 3 minus 1 cubed over 3, which is over 3.
Next, we're going to talk about integration, which is basically the opposite of deriving, which is why sometimes the product of an integration or of an integral is called the antiderivative. So basically how you do that, if you want to find the antiderivative of something, let's say x squared, how you would write that you want to find it is you do this little thing, x squared dx. That's saying you want to find the antiderivative of x squared. So what you would do is, it's the opposite of the power rule, so you would do x to the exponent plus 1, but since the derivative of something you have to, in the power rule you have to take the 2 down, or you have to multiply by that, you want to do the opposite. So it would be x3 over 3, but you also have to do plus c, because since the derivative of a constant is 0, you don't know if there's a constant in there, and if there were bounds to the, on the equation, which I will talk about later, then it wouldn't be plus c, it would be according to the bounds. So another way, it might be if there's a more complicated function, like let's say you want to find the antiderivative of 2x over x squared. You might want to use u substitution to do that, since it'll make it easier. So you want to say, let u equal x squared, and then you have to find the derivative of u is 2x. So basically with that information, you see that the u is present in the function, and so is the derivative of u. So basically you can you can change the equation to the antiderivative of 1 over u with respect to u. And then the derivative of that would be ln u plus c, as we just learned. And then to simplify, or to the answer, you have to plug in the original to u, so it will be ln of x squared plus c. So what can you use the antiderivative for? Well, you can use the antiderivative to find the area under a curve. So let's use, let's just pretend this is the graph for x squared. If you wanted to find the area under the curve between 1 and 4, you would be finding the area of this section. So basically what you would do is, here are the bounds, so you would plug in the bounds. So as 1 goes to 4, you want to find the antiderivative of x squared, which, as we know, would be x cubed over 3, and this is the notation from 4 to 1. So how you plug 4 and 1 into the equation, so it would be plug 4 first, and then minus plug 1 into the equation would equal 1. which is the area under the curve. So another thing we can do by using the antiderivative is to find the volume that a function makes, which is kind of hard to explain, but for this one basically we're doing cross-section, so this is how you find the volume of a function that's turned into a shape. We're going to use a square, so the area of a square is b squared, and the base for it in this case would be x squared, because that's the function. So basically the area that we're finding is x to the fourth. So basically what we want to do is we want to integrate x to the fourth to find the volume of the shape that we are making. So that's x. 204.6. So another way we can find the volume is if we do a volume of the function rotated around the x-axis. So basically we are rotating the shape that this area would make to make a circle out of it. So the equation for that is pi r squared, and r is the function which equals x squared. So the equation that we use now is pi x to the fourth. And so we would write that like pi can go outside because constants can go inside the integral or outside. Pi x fourth dx. 642.769. And then a couple other ways you can find the volume of, or different things that you can use to find the volume is if you wanted to find the volume of, let's say, this right here, rotated around the x-axis. So that is not something that we can use discs before, which is what we did before, because there's a big gap right here. So we're going to have to use washers, and the shape this will end up making looks like this, but in 3D. And so here is the big radius, and here is the little radius, something like that. I don't know. But anyway, so the equation for that would be pi big radius squared, which is the function for the top equation is big radius minus little radius squared, and then the function for the bottom equation, which right here is the little radius. And so that would end up looking, well, this is the equation that you would plug into the integral.
And that's everything we learned this year in Calculus AB. Learn it or not, because we won't need it anymore. Bye!